chat box, please, students and faculty of UNP. And to everyone here, it is my pleasure to welcome you to this webinar entitled SuperMap GIS Application for Oblique Photogrammetry. To jumpstart our event for today, let us hear some opening remarks from Ms. Gacho, student of UNP Department of Geodetic Engineering, member of Agrimensores Club. Ms. Gacho.
To our respective speakers, faculty staffs, and fellow students joining us today, a blissful morning to everyone. First of all, I would like to introduce myself. I am Absidi Gacho, a third-year geodetic engineering student of College of Engineering at University of Northern Philippines. I am thrilled to be speaking to all of you today and grateful for the opportunity to participate in this webinar. It gives me great pleasure to welcome everyone who has come to this session and for you taking the time to come here today. I welcome all of the distinguished speakers and guests who have chosen to share their vast knowledge and experience with us today. Everyone involved in organizing this webinar has worked tirelessly to make it a reality for us listeners. I would like to humbly welcome you to this webinar hosted by SuperMap Software Corporation Ltd. They are well known for the innovative GIS platform software and service provider, and they hold the third largest share of the global GIS market, as well as the first largest share of the Asia GIS market. Today, we'll take a look at the latest developments in the fields of big data, AI, real estate, and smart cities. As Isaac Asimov has said, science can amuse and fascinate us all, but it's engineering that changes the world. Good morning once again, and welcome, welcome, welcome.
Thank you, Ms. Gacho, for those kind and inspiring words. We are also delighted to be in partnership with you in spreading the GIS knowledge. So moving on to the topics for today's webinar, we are going to have two presentations. If you have any questions while listening to the speakers, please feel free to type it in the chat box. The technical team will answer the questions in the Q&A session after the presentations. Our first topic is on the introduction to SuperMap GIS technology and applications on oblique photogrammetry, to be presented by Erica Jane David from the Business Development Team of SuperMap Asia and Oceania Center.
Good morning, everyone. I am Erica from the Business Development of SuperMap Asia and Oceania Center. For my presentation, I will be discussing SuperMap GIS application on oblique photogrammetry, including its processing, analysis, and optimization. First, I'll be giving you a brief company background. SuperMap was founded in 1997 by Dr. Erzun Zhang, and with that, we now have over 24 years of experience in the GIS field. SuperMap is headquartered in Beijing with over 38 branches and offices in China, Hong Kong, and Japan. As of now, we have more than 4,000 employees. This is the China GIS market share in 2015. As you can see from this chart, SuperMap became the top 1 GIS software provider in China since 2015, and last 2019, it became the top 1 in Asia. Shown here is the SuperMap partnership map. SuperMap is already being promoted in the markets of South Korea, Malaysia, Indonesia, South Africa, and some countries in Europe. These are the 5 main key technologies that are the basis for solving spatial problems encountered using the SuperMap platform. We summarize them as BDC. First is Big Data GIS. In SuperMap, we support and handle big data, including streaming data processing, storage management, spatial analysis, and data visualization. Next is artificial intelligence. In 2018, SuperMap released a technology of AI, which mainly provides 3 functions: GeoAI, AI for GIS, and GIS for AI. Our technology supports a Python environment, so your mapping experience is made easier using the object detection tool in SuperMap. With AI GIS, we can also predict or estimate a certain value in the future given a parameter or recreate possible scenarios. AI GIS is also used in making professional thematic maps, saving us time if working on many data. The third one is 3D GIS. SuperMap has been developing its 3D capabilities since 2009, including its integration with 2D and other data models. It's seen construction and spatial analysis. Some of the 3D data SuperMap can support include 3D terrain, BIM or building information model, point cloud, artificial model, water surface, underground pipeline, 3D field, and of course, oblique photogrammetry model, which is the this webinar. And the fourth one is distributed GIS. This one is our new value, just released in the last GTC 2020. We have our capability to manage spatial computing on more than one machine, including for analytics, storage, and visualization. It has 5 components: the distributed geospatial data engine, geoblockchain, distributed geospatial analysis and processing technologies, which supports the big data capabilities of SuperMap, and cloud native and SGIS technologies for publishing our GIS to the web. And the last C in our BTC technology is cross-platform. Our technology can be run with Windows operating system and Linux operating system. Furthermore, your GIS desktop experience can also be displayed and analyzed in your mobile, tablet, and even in web browser. This is the SuperMap products family. SuperMap products ranges from different terminal GIS to SGIS to cloud server. In the cloud GIS server, we have the iServer, iPortal, where you can create your application center, and iManager. Then we have the iEdge, which can help to reduce network latency. And then 2 terminals for desktop, iDesktop, and text, if you want to develop and create solutions based on the SuperMap software. For the components, we have iObjects for C++, Java, .NET, Python, and Spark. Our latest ones are for blockchain and Scene SDKs for game engines. We also have iClient for JavaScript and iClient 3D for WebGL. Lastly, we also have the iMobile and iTablet that you can download from the App Store. We then proceed to the application of SuperMap and Oblique photogrammetry. Oblique acquisition is a bit different with the common acquisition using drone. It commonly uses multiple sensors and capture images from different angles so that the result can cover the whole surface of the object. There are some steps that needs to be done afterwards so that we can obtain a 3D model from it, which we'll discuss further. This is the common steps of automatic modeling from Oblique acquisition. After the data acquisition, we'll do aerial triangulation, then obtain the point cloud. Then process it more to generate TIN or triangular irregular network. Then finally, we can achieve the digital surface model. And eventually, we can get the oblique photogrammetry model. In SuperMap, we don't handle all these procedures, but we can process it after obtaining the 3D model from another software. These are the common standard formats for 3D model. The common ones are OBJ, OSG, OSGB, DAE, and etc. Later, we're not going to directly import all of these tiling files. together, but in SuperMap, we need to generate the configuration file first before importing the data, which also raises the performance of loading the data in the software. Basically, there are so many ways to obtain 3D models. Some softwares already cope with the user's need to achieve a man-made model. However, the manual mode is visual, and the users sometimes need to have a version that is much closer to reality. Therefore, the oblique photogrammetry can be a solution. Other benefits can be achieved as well, including high efficiency to obtain large model from large area, high accuracy since it can achieve high resolution image, and less production cost compared to manual 3D modeling. This is one sample showing oblique photogrammetry data for one city in China. As you can see, we can smoothly display the large data and keep the resolution. So again, if you have any questions while listening, you can drop them in the Q&A chat box and we will answer them later. Oblique photogrammetry involves multiple fields, including hardware and software, flight, modeling, and applications. In the entire oblique photogrammetry industry chain, SuperMap mainly provides basic GIS platform, as well as joint technical support for oblique photogrammetry and GIS. With regards to data production and industry application, SuperMap also cooperates with the partners and work together to provide a joint solution for users. Next, we're going to discuss the methods and how to optimize oblique photogrammetry display with visualization and analysis. SuperMap realizes efficient loading and smooth display of terabyte-level oblique photographic modeling data. At the same time, it supports long-term and stable operation and consumes less hardware resources. Here is another example showing terabytes of data of oblique photograph. There are various methods that SuperMap uses to optimize and manage massive data, such as generating cache, files, using distributed storage such as MongoDB, compressing textures, dynamic projection, and merge root node. In order to improve the loading and browsing performance of the oblique photograph, SuperMap provides a tool of merging root node, which makes the adjacent 4 small blocks merge into one new large block. And it can set the number of merges to reduce the number of root nodes by selecting the level until the performance is optimal. The result will be one configuration file in the SCP format. Next, SuperMap provides a compression tool that compresses texture data from oblique photographic data to texture compression format. And the third one is to generate STM or spatial 3D model, which is suitable for loading the WebGL, which can improve the browsing efficiency. We also support converting OSGB and SCP file to SGM after texture compressions, root nodes merging, monomers, and etc. Our capabilities are not only for desktop terminal, but we can also bring your data to cloud-based platform so that users can publish their 3D data or share to another user online. In order to meet the needs of users, SuperMap GIS is on distributed technology, which implements distributed storage, combined distributed file system, and distributed database, and distributed operator transformation of oblique photogrammetry models, avoiding multiple input and output, and achieving efficient full process management, including data access, data processing, service release, and multiple terminal applications. It helps real-world 3D construction so that it can realize efficient storage, management, and processing of terabyte, petabyte, massive 3D data. With distributed processing, we can increase the processing performance. For example, in standalone mode, we need 21 hours or almost a day, but with distributed processing, it is 7 times faster. Now I'm going to show you some of the operations and analyses that can be used with oblique photogrammetry. For example, is extracting the building footprints. Based on deep learning, we extract the bottom polygons of each building And then by referring to the ground polygons, we can select and highlight each single construction or building, query them, create thematic maps, and do buffer analysis. This is an example for thematic map based on the attributes of buildings. And also, after we do the objectification, we can also do spatial query. For example, if we want to build a new road in the red line, we can identify the areas or buildings that will be affected. Here are the various 3D analyses available in the SuperMap platform, such as a skyline analysis, sunshine analysis, shadow analysis, openness, viewshed, slope analysis, and more. This will be discussed more in detail later during Ian's demonstration. We can also integrate oblique photogrammetry data with other sources of data, such as 3D lines, terrain data, BIM, or building information model. We can also connect with real-time video and Internet of Things devices. We can overlay the video with the oblique photogrammetry. So that's it for my presentation, demonstration on the operations with oblique photogrammetry. Thank you so much for listening.
Thank you, Erica. That's pretty cool, right? Especially the video demonstrations. That was just a sneak peek of the key technologies of SuperMap GIS and its applications for oblique photogrammetry. While you're letting all of that sink in, maybe you can also start pondering on how you can utilize this kind of technology in your own field or industry. We're very excited to hear about what you come up with, and we're very open to collaborating with you to make that happen. Again, if you have questions about what Erica has just presented, anything about the BitDC technology of SuperMap, please head to the Q&A chat box below and our technical team will answer them. Meanwhile, kindly scan these QR codes to access the form for evaluation and attendance. You may also click the links found in the chat box below. The form will be open until the end of this webinar. For our second and last topic, Ian Almazan, a technical engineer of SuperMap Asia and Oceania Center, will be presenting to us a demonstration of GIS applications for oblique photogrammetry using SuperMap GIS technologies.
Okay, good morning. Welcome to the live demonstration part of this webinar. Okay, so let's just start with this PowerPoint presentation. So as shown before, the oblique photogrammetry industry chain involves, of course, the first part, which is capturing the images using your aircraft and your oblique cameras, and then flying your mission, modeling, or doing your photogrammetric reconstruction. And this part is handled by different software. So for this, you would use the usual software or popular software for this would be Pix4D, Agisoft, and some other up-and-coming software. And then after that, you proceed with the optimization, 3D GIS platform and applications. And that is what is handled by SuperMap. So we do the optimization to improve the display of your 3D model, provide you with a 3D GIS platform to actually do your 3D GIS, as well as provide you with the tools that you can use for any application that you may want with your data. So with this, I would like to start by showing you or giving you a peek with the Pix4D part, so we can have more appreciation with the first part before we go into the SuperMap software. actually the data set that we'll be using for the demo. So this is in Mabini, Batangas. So it's here in the Philippines. And let me show you the ray cloud. So this is the aerotriangulation part of photogrammetry. So this is our captured photos, and these are the reconstruction points generated after the aerotriangulation. And afterwards, we create the other outputs such as the point cloud. Okay, so this is the point cloud, so it's quite nice. And then the actual output that we will mainly use for today is the triangle meshes. Okay, so let's just wait for it. So the point cloud that is produced, so as shown before, from the point cloud, we create the thin or the triangular regular network, and then from that we produce our surface models, our orthophotos, and our 3D model. So this is our 3D model here, the 3D mesh. Then let me just show you the different outputs that you can do, specifically with X4D. Okay, so these are the output options. So you have your OBJ. This is some of the most common software parts. File formats for a 3D mesh. And what we're gonna use for this demo is actually this one, the OSGB format. So this is the most common or open source styled format for a 3D model from photogrammetry. Okay, so next I'll show you the actual outputs that we have from Pix4D. Okay, so I exported all outputs in UTM zone 51 North, the UTM zone for the Philippines. So here we have our 3D mesh. As I've said before, we're going to use the OSGB format. But here we have the OBJ format, the FBX, and this is the texture file. So with 3D meshes, there is a separate file for the texture. And by texture, we mean the colors and the colors of your 3D mesh. And this is the dataset we will use. It is a tiled OSGB dataset. Okay, and then for the other outputs, this one you might be more familiar with. This is the actual GIS outputs, or for 2D GIS. So we have our digital surface model, our orthomosaic, and as well as some contours, a digital terrain model. Okay. Okay, so now we can proceed with.
Nakakonect lang siya. Yung messenger yun, sir, messenger.
This is the
Hello, Ian. I think you have a slow connection at the moment. Hello. All right, I think it's okay now.
Sorry.
Okay.
Okay, so now I think I'm already sharing iDesktop. So I've created a file data for GIS outputs. So just import dataset And then let's go through the picks for the outputs that we've browsed before. Okay, so our DSM, or digital surface model, it's a raster dataset because it's elevation. And our orthomosaic, an image dataset. Our digital terrain model, also a raster dataset. And let's also get our contours. And lastly, I also made a building dataset for us to use today. Also import that one. So I think that's all the datasets that we'll be importing. And while we're waiting for it to import, let's copy the OSGB files too. Let's copy our OSGB files to our work folder, just so we have a backup. And now, okay, so we've finished importing our data sets. Okay, so this is our orthophoto, or the correct mosaic of corrected photographs. So with orthomosaics, all distances are supposedly correct already. There are no more camera distortions, or at least it's minimized, especially in the middle. So distortions will only be here at the sides. So we also have our building data set. So as you can see, so we digitize some of our buildings. We also have our contours. So let's style our contours differently. Right. Those are our contours. These are 1 meter interval. And then let's also view our DSM. So the DSM is the digital surface model. So this is elevation data. And as you can see, it's quite rough since it includes the tops of your trees and the buildings. So these ones, these protruding colors are actually your buildings. Okay. And then in comparison, let's view our DTM. And so this is the digital terrain model. So it's quite smooth compared to the DSM, since the DTM is an approximation of the ground underneath your buildings and underneath your trees. That's why it's very smooth. A lot of it is interpolation. Okay, so now that we're familiar with our photogrammetry data sets, we can now start with the task of generating the scene cache for the configuration file. So in our 3D data tab, let's go to data management and generate configuration file. So our source path is the folder containing our OSGB files. So as you've seen, target path, let's see, should be empty. Okay. So let's select this pre-made folder, OSGB config Mabini. Let's name our output. Set our our projection. As I've said, it's UTM Zone 51 North or EPSG 32651. And then let's set our model center. So for mesh data sets or 3D models, most 3D models, it's actually not georeferenced. So it does not contain an inherent projection data or position. It's all based on a 0, 0, 0 position. So to actually display it properly on the map, we need to supply it with its reference. So I have here the coordinates for the middle of our model. So I just extracted this from our outputs. So let's import them or input it and then okay. Yes, so SuperMap says that it's been successful in generating the config file. So let's see. So this is the config file that we generated. So, okay. And the next part is projection transformation. So this is for the kinds of model data that is in ENU spatial reference. So, and then we would like to display it in projected coordinate system. But for us, we already know the center point, so we don't need to do this. So we will move on to step 3, which is opening our scene cache in a. Okay. So let's make our spherical scene. Just right click here and use spherical scene. Okay. Let's also just save our map. So this is our scene. A 3D scene is just like Google Earth. So we're going to display our data on a 3D globe. So to add our cache layer, just right click general layers and add OSGB cache layer. And then browse to our output folder. Okay, and then right click and zoom to layer. So it went right to Batangas. So that just means that the coordinates we used to input are correct. So this is now our 3D model viewed in SuperMap. Okay, I think some parts of it are underneath the ground. So let's raise it a little bit so you can see everything. Okay, so this is the water part. Okay. This is our 3D model. Okay, so the next part is the effect repair. Okay, so I will demonstrate some tools for repairing the 3D model. So just like this one of the main problems actually with photogrammetry is its depiction of water. So as you can see here, the water is erroneously displayed. It's quite spiky. So it looks like there's a tsunami happening all the time with photogrammetry. So let's try to correct this part. Okay, so in the 3D Designer tab, go to OSGB processing. So the first tool that we'll use is texture replace. Okay, so let's draw our region that we would like to replace. Okay, so I'm just drawing the region containing the ocean. So when doing this, make sure you're clicking right on the model, just so you don't click in the empty spaces. Okay, so right click to finish. So, and then we can replace that with a texture. So this is the created temporary region. So it's draped all over our water body, and we can change its appearance. So for example, you can make it red if you want, or blue for water. So you can do that. But there is a more robust solution. So you can use the variety of 3D symbols in SuperMap. So let's go to the symbol selector, go to 3D fill and view the library. So we have quite the selection of symbologies for water. So let's try running rushing water. Okay, let's try again. And this time, let's try calm lake. Okay, so this is calm lake. So as you can see, it turned into a water body. So you can even see the reflections of your mountain side on the water. So I'll just show you rushing water there. So rushing water is a little bit more violent, more dynamic than the calm lake, as the name says. Okay, so let's go with calm lake. Okay, so that's one way of doing it. So you can actually save this, but for our purposes today, let's just go with another tool. Okay, and the other tool that I will show you is the clip. So with clip, you can clip the erroneous parts of your data set. So let's just draw a region. So maybe I think starting here. I'm just drawing the region that I want to clip out. So okay, so this is what you will have. So you can actually use the two in conjunction with each other to create your, still have your water. So you can just trace that later. Okay, you can use them together. Okay, so now back to our data set. Okay, and the next concept that we'll show you is with monomers. So as you can see, in the 3D model that we have is just one piece of data. So there's no distinction about its parts. So with monomers, okay, so what the monomer concept is the application of a vector file on your 3D model. So the vector file can be assigned or clamped to the 3D model so that we can get the monomer. The monomer will help us to achieve attribute queries, spatial analysis, and other stuff. So as you can see in this photo, there was actually attribute assigned to this building in the 3D model. So there are three types of monomers. You have the split monomer, which is based on the object contour vector data to generate the monomer. So we don't have that here. What we have is the ID monomer and the dynamic monomer. The ID monomer assigns existing field from vector data to the 3D model based on location, while the dynamic monomer is clamping of the vector file data on the 3D model. I think you'll appreciate this more once we do it on the software. Okay, so what can you do with monomers? So you can do your usual GIS stuff on your 3D model. So you can query your attributes, you can do buffer queries, even make thematic maps. So that's the advantage with monomers. And what are the GIS applications? So in this example, they use a vector data to add attributes to the floors of a building from a 3D model. Okay, so they overlaid the vector data to make the effect of having attributes in your 3D model per floor, in this case, in their building. Okay, so let's start with the dynamic monomer. So again, this is our 3D model. Now let's add our building data set. So as you can see, our buildings are underneath the model. That is due to the style setting. It's clamped to the ground. So in order to clamp it to our model, let's select the clamp to object altitude mode. So now you can see our buildings are draped on the 3D model. Okay, let's change. We can also style this so it can be better visualized. So let's make it blue. Okay, and then let's add some transparency. Okay, so those are our buildings. So what is the effect of draping the vector layer? We can actually select them just like we do with our usual shape files. Then we can also check the attributes. So this is building number 2. This is building number 1, number 3, number 4, etc. We can also make a thematic map. So let's go to thematic map. Create thematic map, unique value. Okay, and let's select a color. Okay, so as you can see, it's now symbolized based on the building ID number. So you can do that. And importantly, the other main GIS function, we can also do our queries. So in your spatial analysis, select SQL query. So suppose we want to know which is building number 2. Okay, so spoilers, it's already here. So select asterisk. So that's the wildcard character to select everything. So our subject layer is Mabini buildings. We want to query ID number equals get unique values number 2, for example. And we want to show a result by highlighting it in the 3D scene. So query. Sorry, let's do it again. Let's do our query again. Mabini building equal to highlight in scene. Okay, so there, the query is successful and it selected this building. Then let's check. Oh, there it is, actually building number 2. That's the spatial query part. So that's how dynamic monomers work. Next, we have the ID monomer. So with the dynamic monomer, you saw that we draped our vector data set over our 3D model, just like this. With the ID monomer, we're actually going to add attributes on the 3D model itself. So to demonstrate, let's actually do it. So again, in 3D data, use the compression and monomer tool. So we are going to add our configuration file as our input, and then save type S3MB, that is correct. Target path. Let's go to the root of our work folder, and then model monomer. Oh, I'm sorry. So this is the attributes we will add, and as you can see, the ID is not yet there because it only accepts integer data sets. Okay, so let's change the data type of our attributes. Attribute table. So as you can see, the ID is in long integer. So let's change it to int, apply. Okay, so that should be available now to be used as the field for our compression and mono. So again, let's select our OSGB cache file, model monomer, Bini building. So now we can choose the ID field and then set our root work folder. Let's check. Okay. And run the tool. Wait, yeah, my iDesktop actually crashed. Okay, so let's recopy the OSGB file. Let's create a new folder for it. And then let's delete our old configuration file. Okay, so very quickly, let's make the configuration file again. So source path is our newly copied OSGB data. Target path, again, our work folder. Let's name it config. Sorry, this is the first one. So output folder is OSGB copy module. Set the projection. And then set the center for it. Okay, let's edit the scene again. Okay, then again, let's run the compression and monomer tool. So let's add it again, and then select our root work directory for the target path, and then select Mabini buildings and ID as our model monomer. So okay, let's run it again. Okay, so this time it actually ran successfully. So this is the produced file. It's of the same name in the root directory as we've selected. So I'll also show you what happened to our OSGD file. So after the first crash, that's why I recopied. So at first, so this is from the fix for the output. So you can see it's still .osgb on the original output, but now it is in .s3md. So SuperMap already converted your data format to be, of course, to have the ID monomer and to be more suitable in the future. So the S3MD file, as discussed by Erica, is the ideal data format if you will use this in SuperMap's online platform. Okay, so let's load the new configuration file. Okay, so as you can see, there's actually a query here. So if we're clicking here on building number 1, it actually shows the building number. So that's the ID monomer at work. Okay, let's move on to the next part. So the last tools it will demonstrate is actually the 3D analysis. So if you attended the previous SuperMap SMC, we also demonstrated some of these using extruded building data, but this time we will be using photogrammetry models. So it's a little bit more sophisticated, and let's get into it. So again, let's use the original model. So as you can see, let's try the view shed analysis first. So 3D analysis. So let's start with our favorite tool, the view shed. I think it's a radius compression. So if you were to stand here, so the green areas are the visible ones and the red areas are the invisible ones. So as I was saying earlier, you can see a drop in quality from our 3D model because of the compression applied by the compression and monomer tool. So I think it's better if you can appreciate it more if we can use a uncompressed 3D model. So let's just make another configuration file. So this time let's use the root OSGB files. And then let's add that newly created OSDB. So it's much higher resolution. a road with a wall over here. So let's do our view shed there. So there you can see the green parts on the road since it's level ground. And then here there's a lot of red since the wall is quite high. And the view shed vantage point is only 1.8 meters above the ground. So if maybe you can jump very high, maybe you can jump 5 meters. So there. Now you can see the tops of the building, so you can see over the wall. Or if you can jump even higher, let's say jump to 20 meters. So that's what you will be able to see from this vantage point. Okay, and I'll also show you view sheds other cousin. So dynamic view shed. So this is what can you see if you were walking down this road. So this is a simulation of a person walking down the road. As you can see, that's the person. Okay, so that's the dynamic view shed. And I'll also show you one of the other favorite tools. So the profile analysis. So in engineering, we always do profiles. So let's do it here as well. So let's raise our 3D model a little bit. This is our profile analysis. So if we make a profile line, just like that. So this is our line underneath, and this is the trees on top. So we're using, that is the data from our 3D model. So just to demonstrate, let's also try it on the road. Try a profile analysis of the road. As you can see, it's quite flat, of course, because it's a road. And then next, we're actually going to make a new 3D scene for the other. So let's save this. Okay, step one to save. So let's make a new spherical scene. And this time, let's add our GIS data sources. So let's add our orthomosaic first. Again, zoom to layer. So that's our orthophoto. You can see it's just a photo, just flat on the ground. And once we add our DPM as a terrain layer, it supplies the terrain for our model. So as you can see, it's quite smooth. As I've said, the DPM is an approximation of the ground, hence the smooth texture. So what happens if we add the DSM as the terrain? Okay, so this is what it looks like if it's the DSM. It looks much like our 3D model from before, albeit a little bit rougher. This is grid data. Okay, so let's use the DSM for now. So I added these data instead of the 3D model because I will be demonstrating these three tools to you. So if you hover on it, it says that supports grid terrain. So it only supports grid data sets for terrain. So we have the DSM and DPM for that. So let's start with the isoline analysis. So isolines are just another term for contour lines. So let's select our area. Okay, so yes, you can generate some contours at 25-meter interval. So let's select a more a smaller interval. So at 5-meter intervals, so these are the generated contour lines. So you can also dynamically switch to DTM. So here, as you can see with DTM, it's flat, smoother, the contours. Just like the contour data set we got from Pix4D. Okay, so let's stick with the DSM since it's a little bit more fascinating. You can also see it wrapping around the trees. Okay. Then next, I will show you the flooding analysis. So let's demonstrate it for the whole area. Okay, so this is a simulation of a flood happening from the minimum altitude on the model, which is 5 meters, up to the maximum, which is almost 170 meters. Okay, so we can also change the parameters. So if we make the total animation time just 5 seconds, then we want to see what areas will be inundated at 100 meters height flood or up to 100 meters above mean sea level. So that's the answer. So let's simulate it again. Okay, so that's the flood simulation from the lowest altitude up to 100 meters. So that's 100 meters altitude. So as you can see, this house is probably the only survivor of such a high flood. And saving the best for last, I'll show you slope and aspect analysis. So this is quite exciting. So let's apply it to the mountain face right here. Okay, so this is slope. So the color ramp is orange for very high slope. So I can attest to you that this is real. This area really is very, very slopey. So that's correct. And then you can also try aspect. So if you can see, you actually have your arrows. So those arrows represent flow direction. If you pour water, then lastly, you can display both of them. So slope and aspect. So that is the flow direction of a fluid on this surface. Okay, quite nice. And you can also animate it. So there, you can see it flowing. Okay, so these are some of your usual hydrology functions you will use in GIS. So, okay, so let's see that's actually the last of my presentation or live demonstration for today. So let's end it while looking at this. Thank you for attending today.
Wow, that's an amazing demonstration by Engineer Ian Almazan. I hope we got you excited and amused with the functionalities of the software. Well, thank you very much, Ian, for sharing with us the demonstration of the functions of SuperMap iDesktop. So there we have it. Our speakers just gave us a comprehensive presentation of SuperMap GIS applications for oblique photogrammetry. We hope that by this time, it is bringing you some new ideas on your current projects, research, or business. So I think while the presentations were ongoing, our technical team has already actually answered your questions. But in case you would like to ask more, feel free to send us a message. We hope that this webinar has sparked your curiosity about SuperMap. We're happy to announce that we will be offering a free trial license to our participants here. Certificate of attendance will also be given after submission of output using SuperMap iDesktop or iDesktop X. No worries, because we can also share with you the sample data that was used for this demonstration. Just send us a message or an email, as you can see on this slide. To cap off our event for today, let us hear some closing remarks from Ms. Griselda Alimangohan, student of UNP Department of Geodetic Engineering, member of Agrimensores Club. Ms. Griselda.
It was indeed an honor to be able to join this webinar in partnership with the SuperMap Software Limited Company. I would like to take this opportunity to thank our dynamic speakers, Engineer Ian Almasan and Engineer Erica Jane David, for imparting us the knowledge about SuperMap GIS application for oblique photogrammetry and how beneficial this information to us, geodetic engineering students. I hope that you may continue to be a living torch of inspiration and source of education in this specific field. And to my fellow students, I hope that we all have enjoyed this webinar and most importantly, learned ample things. Once again, we would like to extend our sense of gratitude and appreciation to all of the people who have made this event possible, especially to our instructor, Engineer Nereo Kerubin, and to his fellow engineers, and to all of us. This has been Griselda Alimanguhan, a third-year geodetic engineering student at University of Northern Philippines. Enjoy the rest of your day and blessings to one and all.
Thank you, Ms. Griselda. We are equally thankful for this opportunity to partner with your university in this webinar. And yes, we will continue to bring GIS knowledge to everyone. So thank you so much, everyone. We highly appreciate your attendance today. Feel free to visit the SuperMap website to get more information about the company. We also invite you to follow SuperMap GIS on Facebook, Twitter, and LinkedIn because we are constantly posting about the latest GIS trends and what SuperMap is currently up to. For the students, SuperMap is offering an open internship program. You might also be interested to become one of our university ambassadors. You will become part of the SuperMap team wherein you will represent your university. More benefits are indicated on our Facebook page, so make sure to like and follow SuperMap Philippines. Again, thank you for attending this webinar, everyone. Don't forget to answer the evaluation form and the attendance form, which you can find in the chat box, so we can bring you a more improved webinar experience. Expect your trial licenses and certificates after output submission in a few days via email. SuperMap will hold more webinars on more topics soon, and we hope to collaborate with more universities in the Philippines. We will virtually see you soon in the next webinar. Goodbye and have a great weekend.